All right, when we talk about computers, computer science, really coding in general, any way that a computer communicates, really any input output, any information that's passed along a computer can only be sent as one of two signals, and we've talked about this before, and that's our binary. So it's either going to be a 0 or it's going to be a 1. We've talked about this in terms of on and off, with 0 being off, 1 being an on. We've seen it in VEX where buttons either return a 1 or a 0. And up to this point, really, that's the only place we've seen binary used. But and you've probably seen it on TV shows, all kinds of things, where the big code pops up and it's just a bunch of ones and zeros, and the computer's making sense of it and doing a bunch of things and programming this and that and everything else. But what that really derives back down to is, in its most simplest form, are binary numbers. We've got to understand what a binary number is. And all a binary number is some sort of some sort of combination of ones and zeros. If we look in the chart up here, there's 15 numbers. These are the first 15 decimal numbers, well, 16 if we include 0. The first 16 decimal values, all shown with their binary equivalent. So if we look up here, for 0, which is obvious, the binary equivalent is 0000. For 1, 0001. For 2, now this is where it gets weird, 0010. So if we look at 2, the binary equivalent is 0010. And the best way to think about this is every time you slide over, you're doubling your value. So if we look at this, we can think of this as how many ones this number has in it. This spot is how many 2's a number has in it. This spot, since we're doubling it, is how many 4's a number has in it. And this spot would be how many 8's a number has in it. So if we look at the number 2 again, it is 0010. That means it has 0 ones, it has a 2, no 4's, no 8's, so the value of it is a 2. Now, that same thinking, if I throw the number, actually I'm not going to tell you the number, we're going to figure it out. If I put in there 1011, now we don't look at the chart, don't look at anything. What we're going to do is come up with the decimal equivalent. We know that it has a 1, so we'll put a 1 over here. We can see here it has a 2, so we'll put a 2 in there. We can see that it does not have anything holding the 4 value, and it does have something in the 8's value. Okay, so we're going to do 1 plus 2 plus 8 gives us a decimal value of 11. And if we look here, 1011 is in fact 11. So when we're thinking about binary, it's no longer a decimal system, which is what we're used to, which is base 10. We're thinking binary, which makes everything base 2. And it's more of a placeholder than anything else. So we're used to having our ones position, our tens position, our hundredths, our thousandths, our 10,000ths, our 100,000ths, our millionths. Instead of having that now, when we talk binary, it goes our ones position, our twos position, our fours position, our eights position. The next would be our 16s position, 32nd position, 64th position, 128th position. And now the pretty interesting thing about it is, if we would have all ones here, so let me get rid of that 0. If we would have all ones here, 1, 1, 1, 1, 1, this would give us a total value of 255. Now, if you think any equivalents or anything where we've used 255, that number may not sound familiar, but we have used from negative 127 all the way to positive 127, which is a possibility of 255 different numbers with our VEX motors. So each of these little spaces here, these little numbers, either ones or zeros, is called a bit. A combination of 8 of them is called a byte. So every time that we are sending some sort of number to that motor, it's actually sending one byte of information, and it's telling it what speed to put it at. Little fun fact for you: 4 bits is actually called a nibble. So we've got a bit, 4 bits is a nibble, 8 bits is a byte, and that's how we convert and exchange information. If you would look up the ASCII tables, ASCII, you'll also see that those are used by, or that information is sent by using binary equivalents. So the third digit on an ASCII table means something. So if you're talking about that, you would send a binary 3, which would be 0011. Now you guys are going to use this information. All I want you to do today, you're going to be converting between binary and decimal. And those of you that get pretty good at it, you're going to look at hexadecimal, and you're going to look at octal, which are very similar in the way that we're using them. They're either base 8 or base 16. And if, as you look through the notes, you can kind of work your way through that and see how you can represent numbers using different notation and using different bases. We're going to talk about this on Friday. We're going to look at binary and see how it's used with colors. So our RGB values, how we can send a byte of information to represent a certain color. So today, that's what I want you working on. Try and convert between binary and decimal, and see if you get to a point, and you can look in those notes, see if you can work into hexadecimal and octal as well.